All right, here on example one, we're going to practice doing sums and differences of cubes. Now, you might wonder, why do I need to know how to do sums and differences of cubes? When am I going to do that? Well, one answer would be that if you are doing anything in three dimensions, so anything describing the physical world in three dimensions. So let's talk about, like, maybe you are taking the volumes of objects and you're trying to add them all up or find the difference between the volumes of objects. Well, volumes, being three-dimensional things, can be described as cubes. I want to remind you that, like, any number in two dimensions can be described as a square. So, like, if I want to do the number 136, I can describe that as the square root of 136 squared. So any number can be described as some other number squared. Okay, so that kind of works in two dimensions. You can describe any sized thing in two dimensions as a square. It doesn't matter whether you start out with a square. So if you start out with a rectangle, there's a way to take this rectangle and cut it up and paste it together until it's in the shape of a square. So kind of imagine like these numbers or these shapes as like pieces of Play-Doh or something. Like I can rip them apart, I can push them together, I can squeeze them, I can squish them, I can move them around. I have the same amount of Play-Doh altogether, but I can kind of move around the shape of how I look at it. So in two dimensions, I can take any amount, any sized object, and I can squish it into the shape of a square. That's why it's important to understand how to do algebraic operations with squares. The same thing is true for three dimensions. I could take any object, so take like the Earth. I could squish the Earth into the shape of a cube, and then we could use our understanding, which we're about to do, of how to do operations with cubes to be able to describe the Earth and things you could do to it. For example, like if you think about the formula for a sphere, if you know this one, well, the formula for a circle is pi r squared. It depends on r squared. It's a two-dimensional object. It depends on something squared. If you do the volume of a sphere, it's 4/3 pi r cubed. So you literally describe a sphere as some fraction, some 4/3, some kind of a little bit bigger than one multiplied onto a cube. So when we describe things in three dimensions, we describe them kind of our basic description is a cube, and we've done something to it. It's bigger or smaller than by some coefficient. Same thing in two dimensions, we describe squares. These are kind of the basic things that we operate with. So we want to be able to use cubes, squares. Those apply to two and three-dimensional objects. Higher level dimensions, kind of more abstract stuff, we can figure out how to do that later. But for now, getting mastery over two and three dimensions, we want to be able to use squares and cubes in our math. Okay, so if we want to add two three-dimensional things, so two cubes together, we're going to use the sum of cubes identity. If we want to find the difference, we're going to use the difference of cube identity. I can show you a picture. I'm going to show you a picture real quick of the difference of cubes first, because this is one that I can describe pretty well, pretty quick. Okay, up top is showing the difference of squares. So you have a squared, b squared. You take away b squared from a squared, and you rearrange the pieces to get a minus b times a plus b. That's our difference of squares proof. Now, difference of cubes looks a lot the same. We have a cubed, b cubed. We take away a little b cubed size chunk from a cubed, and we end up with three different pieces we want to look at. Each of those pieces has one side length, one factor that's this little blue line. That blue line is a minus b. So each of these three things is a minus b times something. If we look towards the end, we get a minus b times three different things: a squared, ab, and b squared. Well, the first one is a minus b times a squared, the little orange volume. Then we get a minus b times ab, the purple volume, and a minus b times b squared, the blue volume. Okay, so that's a squared, ab, and b squared. A squared, ab, b squared. Okay, so just like the difference of squares, like I was saying, how we can cut these objects apart, we can kind of squish them, move them around, rearrange them until they're in shapes that we want to work with. you can do that with two squares to rearrange into this nice rectangle, or you can do that with two cubes and rearrange it into these three rectangular prisms. Okay. Now, the sum of cubes is a little harder. I'm going to link to a video right below this video that's like 3 minutes. Somebody else describing it. They've got the ability to kind of move these things around and show you visuals a little better. But in the end, it's the same sort of thing. We're just chopping up our shapes, rearranging all the pieces, and finding a different way to write it. That's where these identities come from. Now we can take this and we can multiply it together and prove that these two give you a squared minus b squared, or sorry, a cubed minus b cubed. However, that's not how the first person did it. That's just kind of like, that's reinforcing that it's true, but it doesn't really prove it, or it doesn't really tell you where it came from. Where these ideas came from mostly would be through these geometric manipulations. I could be wrong on my math history. Maybe somebody was able to do it just algebraically first without ever thinking about the actual physical things they were describing. But for me, I understand things best visually. I understand them best with representations like this. So I hope you guys can follow on with that as well. Okay, so let's look at this. If you recall, based off the previous list, our identity for the sum of cubes is that a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Okay, so I'm just going to put the right side of that. So we're doing sum of cubes, a squared minus ab plus b squared. All multiplied by a plus b. Okay, so that is our sum of cubes factored down. We use these terms, we use identities, and those identities are basically a mathy way of saying that, like, we know that this is equal to a cubed plus b cubed, but it's a little hard to show why, and sometimes we're not going to want, sorry, I don't have room here. Sometimes we're not going to want to show why, so we might just have a list of identities that we can go to and use as kind of a reference guide. Okay, so what's happening here? They say that these two terms are going to be our cubes. Well, they're not cubes yet, so we need to turn them into cubes first of all. So 8x cubed can be 2x, that quantity cubed, and 125y to the 12th, gosh, what's that going to be? That would be like 5y to the 4th cubed. Okay, the 4 to the 3rd power gives us the 12. The 5 cubed gives us 125. So now we have our a, which is 2x. So a is our 2x. B is our 5y cubed, or sorry, 5y to the 4th. And then we just plug it into our identity. Okay, so we get a plus b, 2x plus 5y to the 4th, times a squared, 2x squared, minus ab, so we put the terms in there, plus b squared. All right, so all of this part is here, and this first group is the a plus b. Okay, so 2x squared, we know that as 4x squared. I guess I should say the quantity 2x squared is equal to 4x squared. And the quantity 5y to the 4th squared would be 25y to the 8th. Okay, the 5 gets squared, and the y to the 4th gets squared. At this point, this is our final answer. This is our factored form of this sum of cubes. Okay, now the difference of cubes, I'm going to leave all this up because there's only a little bit I need to change. The difference of cubes ends up switching two of the symbols here. Rather than a minus sign here, we end up with a plus. And rather than a plus sign here, we end up with a minus. Okay, so I just want to reiterate, these equations are not things to memorize at this point. There are identities that we can look up, but I do want you to understand, if anything you take to heart, is that the way that you can come up with these is by taking geometric objects and looking at how you can manipulate them. Okay, so down here, we'd want to say we have 54x to the fifth minus 128x squared y cubed. Okay, so first we're factoring out a greatest common factor, because if that's possible, we always do it first. So there is a factor of 2x squared that can be pulled out of both of these. That leaves us with 27x cubed, which is the same as the quantity 3x all cubed. 64y cubed would be, what do we think that is? 4 times 4 is 16 times 4 is 64? Yep, so I think that would be 4y cubed. If I had only been smart enough to look over here, I would have seen that that was already spelled out for me. Okay, so the difference of cubes, we're just going to plug it into our identity, right? We're just going to say this is my A, this is my B. My A is 3x. That's my A. My B is 4y. And when I put it all in and simplify, the only boxes we have left here is to put 3 and 4. It makes 12xy. And 4y squared, we square the 4. We square the y. And we have our factored form of this difference. So once again, we can take any sum of cubes, any difference of cubes, and turn them into products of some factors. We can also take things that don't even look like cubes and manipulate them so that they are, so that we can use these properties. All right, that is it for example number 1.